So today we'll be going over these Bayesian things, and then next time we'll put those to use and learn about naive Bayes, which is another supervised learning algorithm that we're going to know about. So let's see here. Okay, so let's talk about what Bayes nets look like. All right. So here's the first part of a Bayes net. So Bayes net has these variables, so HA, USB. And those could be, in most cases that we're going to talk about, these are going to be Booleans, so true or false. So in this example, we're talking about MIT, and here I write these things down. So it says H stands for there's a hack on campus. A stands for there's an art exhibit. U stands for uniformed police. S stands for sculpture. And B stands for business people. So we're going to deal a lot with probability. So we're going to talk about the probability that there's a hack on campus. So it could be there is a hack or there's not, and the probabilities relating to that, right? And so here in the Bayes net, we have these variables, and we have them related with these arrows. And so you can think of these as almost being like causation relations, but they can also be correlation. So what I mean by that is this arrow here is telling us that maybe if we know something about if there's a hack on campus, it might help us determine whether there is uniformed police officers on campus. Okay. Now the same is true in the inverse. Just because these arrows point one way, we can also think about if we know that there are cops on campus, we might have some suspicion that maybe they're there because of the hack. And so maybe that can help us think about whether there's a hack or not on campus. Okay. So for those of you guys coming in a little late, so we're just talking about Bayes nets. So here's a Bayes net. Here are the variables in my Bayes net, represented them with the first letter. We're talking about how if we know something about one of these nodes, using these arrows, we might be able to figure out something about the other nodes. So my example was, if I know that there's a hack on campus, it might help me determine whether there are uniformed police on campus. And the same is true in inverse. If I see some cops around, maybe they're there because of the hack. So I might be able to guess something. So that sounds a lot like we've been doing so far, which is we have some information and we're going to use it some way to make a good guess. So that's where it's going to fit in later. So next time when we talk about naive Bayes, that'll be where we take these ideas to be able to classify some stuff. Okay. Now let me just pull up my notes real quick so I get these numbers right. So there's another part of the Bayes net that I haven't drawn yet. And so we have this kind of topology, but as I said, these are really dealing with probabilities. So we have to have some way of expressing the probabilities that are in this graph. So for instance, the probability that there's a sculpture given some other information. Maybe the probability that there's an art exhibit just by itself without giving anything else. So let's talk about those. So let's see here. So I made some numbers. These are from, so I'm actually going through some of the notes that are on the OCW page, and it's covered in fall 2010. So if you want to see this example again, you can look there. So you can just search like 234 OCW. It'll come up, and you can find 2010 and look at the tutorial for that. Okay, so there's these other things. So we have our variables. Let me just quickly mention we have events for our variables. So hack could be, hack could be true, or hack could be false, or hack could be true and business people could be false. So these are like events, right? This is like one day this happened. That's kind of how I like to think about it. So that's just vocabulary. So these things are variables, and an assignment to those variables like this, like a group. These things are like events. All right. Now there's also things called conditional tables. And so I like to put those like straight onto here, and you'll see that done a lot. And so, for instance, we could talk about the probability that H is true. And we might give that, 5% chance that there is a hack on campus today, right? Now I could also put the probability that H is false, but we know the probabilities have to sum to 1. So we just know it's 95% chance false. So I'm not going to put that column there, okay? Now we can also do the same for U, but now the difference is with these arrows, we're going to take into account our parents and all of our ancestors in order to make the tables as we go down. So for this one, we're going to say, what's the probability? So this is H, and then this is the probability of U given H. And so H might be false or it might be true. And now if, so I gave some numbers to these also. So this one is 0.1, this one is 0.5. So what this is saying is if there's a hack on campus, there's a 50% chance that there are going to be cops around. And if there's not, there's only a 10% chance that there's going to be cops. Okay? And so you can see this helps us answer questions in the form of if something about this, then we can conclude something about the child. So if something about the parent, then conclude something about the child. So we can directly read those off from this chart. If we want to move the other way, if we want to answer something about the parent given the child, we have to do a little bit of manipulation. And we'll come back to that when we talk about these other probability stuff. That's just a bunch of math that we need to get under our belts. So now let's talk about this S. So S is going to be in terms of H, in terms of A, and then it's going to have some probability of S equals true. Let me give myself a little more room. And let's also make this H equals true. Sorry, U equals true. Okay, there we go. So here I have H, I have A, and then I'm going to have the probability that S is true given whatever I have for H and A. Okay. And so I could have both of them be false. I could have false true, or true false, or true true. And so I have some probabilities for these as well. So this one's 0, 0.8, 3.86. Okay. Similarly up here, we have some probability for A is true. And that's just going to be 0.025. And then for B, we also have A as its parent, and then we have the probability that B is true given A. So false, true, 0.5, 0.3. Okay. So these things are called the condition tables. All right. So this is pretty much, this is a Bayesian right here. So it's got the topology and then it's also got these condition tables. So my goal is to make you guys be able to totally understand this and answer questions about it. So you should be able to tell me if there's a hack on campus and there's no businessmen, what's the chance that there's a sculpture on campus? Those are the sort of questions we're interested in asking here. Okay. So let's talk about let's just write those down. Goals. So we should be able to answer these sort of things. What's the probability that something occurred? And this is a shorthand. I'm really talking about like X being true, right? But I'm just going to write given. So what's the probability of a sculpture, right? Or what's the probability of a businessman? We're also going to talk about conditional probabilities. So it's the probability of something given some other information. Now there could be a lot of these, right? There could be like Z, there could be more of these, right? And then we're also going to talk about joint probabilities like this. So it's the probability that all these things are true, that x is true and y is true and z is true, or that x is true and y is false and z is false, right? So these are kind of our three goals that we want to be able to answer. All right. So the interesting thing here is we have some of these, right, all the way at the top. We have P of H and P of A. And then the rest of them kind of look like these sort of things. But now the question is, like, how would I do something like, given those probabilities, how would I answer something like probability of A given S is false, B is true? So how do I answer something like that? So here's could be like one thing in our goals. How do we answer something like this? And so what we're going to do is we're going to go over some probability that's going to let us use these expressions and change them around and be able to answer this mathematically. Okay. Let me just make sure that's all showing up. Okay. Okay, so let's talk about the types of probability that we're interested in. And then over here on the side, I'm going to write down our important equations. So first we have the joint probability. And so that's going to be something of the form probability that mu1, and we're going to have a bunch of these variables being assigned. Okay. That's what that thing looks like. And we actually have an important equation for it. So there's our first important equation. Okay. And so we could ask maybe, what is probability of H, A, U, S, B in our example? So we can use that equation over there. And what I'm going to do is I'm just going to multiply out those probabilities. So I'm going to take the first one, P of H, given its parents, but doesn't have parents, so don't have to write anything there. Okay, next one, P of A. Its parents, it doesn't have any. And then probability of U, its parents H, probability of S, its parents H and A, and then the probability of B, its parent A. Okay, so there's an example of how we can apply that rule number one to our Bayes net here. All right, and we can actually calculate this out. So you can see we didn't just like do this for no reason. We did this because now these things are things we can just read off of our Bayes net. We can just look at the condition tables and we have P of H, we have P of A, we have things like P of U given H, right? P of U given H. So these things right here are all from our Bayes net. So that's what we want to try to do, is we can take the expressions that we want to answer and try to make them of the form where we can just read off values from here and just multiply them out or add them together. Okay. All right. So now comes the next one, which is marginalization. So marginalization is like taking the probability of just a couple things. So let's say we have variables A through F. What if we wanted to know the probability of A, B, C, but not D, E, and F? So we want to kind of ignore those ones. We don't want to think about them. So that's what marginalization is going to allow us to do. So we have an important equation for marginalization. So let's say we only care about everything from A to B. So you could say this is like some chunk of all the variables we have. And what we're going to do is we're going to sum over all the ones that we're not concerned about, all the ones that don't show up here, over the entire So this is our entire joint probability. So this is all the variables in it, and this only has part of the variables in it, and this is the subset that aren't in it. Okay. So let's take a look at something like that. So what happens if I just want probability of S, so some subset of HAUSV? So the probability of S, I can look at this equation over here, equation 2, and I can say, okay, well, I'm going to sum over H, A, U. I'm not S because I want that one, and B, the probability of H, A, U, S, B. Okay. And now we know how to manipulate this thing. That's just from this joint. We expand it out. H, A, U, B. And I'm just going to put this thing over here. This right here. I don't want to have to write it out and spend your time doing that. And now you can see some of these terms in here have A's and some of them have H's and U's, and these sums, this sum right here, this is just a shorthand for 4 sums over H, A, U, S, and B. Right, so I could have written 4 of these things out. H, A, U, B. Okay. And because not all of these have H's and A's and U's and B's, I can kind of move things around in here to make it a little easier to do the math. And we can get something like sum A, Q A, sum over H, Q H, Q S given H, A, sum over U, H, and I'm missing B. B, probability of B, A. Okay, so I can get something like that. Now let's talk about a little bit about what these sums are doing. And it's just like, well, where did this come from, right? So when we're marginalizing something out, okay, so this is what I mean. What about the probability that B is true? Just B is true. Okay. Now intuitively, if we have A, we could think about it as being like the probability of B equals true when A is true. There's another possibility, which is the probability of B equals true when A equals false. Let's just assume we don't have all this other stuff over here. Just think about these two. So I could sum these up, and now I can get the probability that B is true. Okay. So that's what these sums are doing, is they're kind of iterating through all the values of these given then expressions. Okay. They're adding them up, and then that way we don't have to care about them. We can get this P of S. Okay, so let's so we notice 2 things. Notice that the sum B, P given A is just 1, and that the sum U P U H is just 1. So for some value of A, what's the probability that B is true? And for that same value of B, what's the probability that B is false? Well, those are the only two options. So it's got to be one of those two, which is why they add up to 1. Same sort of reasoning here. And so this stuff actually simplifies a lot. So we can get rid of this thing. This thing is just 1. And then this thing is just 1. Okay. And so we actually get just things of like this form. So let's just write that out real quick. So we get PS equals PH. And so I'm going to write, whenever I write, there's an alternate notation to saying like equals true. You can also just put H, and it means true, and then if you put a bar over it, it means it's equal to false. So I'm going to use that notation just to be a little more compact. Okay. So there's one where A was true and H was true. Then we also have one where H is true, sorry, H is false, but A is true. We also have one where the probability of H is true, probability of A is false. And we also have one where they're both false. Okay. So that's what these two sum things we're doing. Okay, cool. So there's the marginalization. Let me make sure that's gets on camera. Okay. All right, and then there is one final quick point, which is conditional. Which is something like what happens if you have pxy. Okay. And so some of these we're really lucky, because if we have them in the form of child, or child, parent, really lucky, we already just have those in the truth table, so we can just read that right off, right? So if we had this probability of S equals true given H is true and A is true, we can just read it right here, 0.86, right? But what happens if these get swapped around, or if this is a parent and this is like a descendant, or so how can we deal with these in general? So we need some equations to deal with these. And so the first one, it's called the chain rule. And then from the chain rule, we can actually get this other expression. So this is chain rule. This is Bayes rule. And hopefully those show up. Okay. Awesome. So now these are pretty awesome because they let us swap these x and y guys and just scale it by some px and py. Okay. All right, so I'm going to erase this type of probability that I have written up here. Someone's got a question about it. Okay. So now we have all this math. Let's really quickly cover what an ancestor graph is. Ancestor graph. So an ancestor graph is when you have some variables you care about. So let's say we have something, like, let's make up some letters. So maybe this is a different Bayesian with these variables in it. And I want to know the ancestor graph for this thing. And we have, the Bayesians over here somewhere. So maybe we have something like this. And this one is E and C and D. And I'll just call this A, B, Q or something. Okay. So what does the ancestor graph look like for this? So ancestor graphs, all you do is start at all the points that are in your expression, and then you only are allowed to move upwards and try to reach everything you can. So go this way. Now I'm here. Okay, move upwards, I can't do anything. This one I move upwards here. Okay, move upwards, I can't do anything. And so these ones that I've like quadruple circled are the ones in the ancestor graph for this expression. Okay. Now the ancestor graph is useful because I'm going to teach you guys now, with all this math we have, remember that our goal was to take this and be able to answer any question like, what's the probability of sculpture? What's the probability of, this given that, with all the variables I want thrown in. And so I'm going to give you a general way of doing that, but it's going to rely on the use of an ancestor graph. Okay? So we're going to use all this stuff together now. So now let's talk about the general method. General method. So let's talk about for P of x. So how do I calculate P of x? So there's only a couple steps. So the first thing, just draw this like this. Okay. The first thing is to write P of x as a marginalization. Now we know we have some expression for that. That's equation 2. So basically it's saying use equation 2 to get something of the form P of x equals other stuff. Okay. Next step. Expand to conditional table probabilities using equation 1. So that saying is great. Now we have P of x. But now what I want is to use this sort of thing and get P of x to be represented in a way that I can just read some values off of this. Okay? And we know that that's exactly what that joint distribution equation does. It puts everything in terms of their parents, which is exactly what we have here. So that's all good. So we're going to use equation number 1 to do that. Then we're going to cross. So this is a, you could just do this and then solve. You could just do up to this step and solve. This step right here is just going to let you know how we noticed those things canceled out earlier when we did that giant equation. We had those two things just be 1. So this step I'm about to introduce here is going to let us skip some of that work by noticing that sort of stuff for us. Okay. So we're going to cross out, ignore terms not in ancestor graph of x. And in my example, I had chosen P of s. And you notice here's P of s. And if we have its ancestor graph, we get h and a, but we don't ever see u and b. And exactly the two sums that were over u and b were the ones that equaled 1 before. So the ancestor graph notices that for us. So we can do this step to not have to do that math. I'll have to remember that. Then all we do is we just like solve, simplify, whatever you want to call it, to get our expression for p of x. Okay? Awesome. So remember, this is just a shortcut. We don't need to do it. We can just do the math ourselves, but that's a nice thing to do. Okay? Okay. So I'm going to erase this ancestor graph. And just to recap it one more time for E, C, and D. E, C, D. We move up. We get to Q. We get to C, but we already had C. Nothing else up higher. We can't reach B. We can only reach it by going down. Same thing with A. So those don't show up in our ancestor graph. So it's just the circle ones. All right. Okay. And now let's talk about how you do P of x, y. It's going to be very similar. So we're going to start out by writing. Okay, so the first thing we're going to notice is this thing. We like using equations 1 and 2 because this helps us deal with partial things, and this helps us put those partial things in terms of their parents and then just read off the chart. That sounds all great. But what about this given then? How do we deal with that for equations 1 and 2? So the way we're going to do that is we're going to use the chain rule or the Bayes rule, and we're going to be able to get these sort of things as some sort of joint. Then we're going to put the joint, a marginal, because this might not be all of them. We use the marginal one from the joint, and we're going to use the joint into here, and then we'll be able to go all the way back and find out what this was. Okay, so we're just going to use these three equations, and maybe the Bayes rule if we have to do some switching around. That's intuitively what we're doing. So what we're going to try to do is we're going to say, okay, this is going to be P of x, y over P of y. And so now all we have to do is we have to do this, but for this part, and then do it again for this part, and then just divide them. Okay. Using general method. Find P of y using general method. And then just divide them. Divide and simplify. So I'm going to write this P of x here. Really, this is like, this x could be multiple variables, so I guess that's not a very nice notation, but this is kind of the same way that you would do something like P of y, z, right? You just write out P of y, z as a marginalization. You use this to do that. You just do this whole thing the same. So this doesn't cause any problems, the fact that there's two variables. We can still use this method to do it. Okay? So I guess this really looks like more of a marginal than, it might not only have one variable, it might have more, but that's okay. You can still use that equation. Okay. Cool. Let's see, what have we covered? Okay, and then the last point of intuition I just want to talk to you guys about is, if you remember at the beginning we were talking about how it was really easy to read off if there was some uniform cops. If there was a hack, we could find out the probability of uniform cops. But what if we want the other way around? What if I saw some cops walking around and I wanted to know if there was a hack going on? And so that is just asking, well, I saw some cops, so given that there's some cops, what's the probability of H? And see, we have probability of U given H, but not H given U. So all we have to do is apply this Bayes rule, get this thing, so it's in terms of this guy and these two. And now these three things, we know how to do those. So we can solve for each of those independently. And then we can finally get back the one we wanted. Okay? There's a little bit of extra work there when it's backwards because you have to switch it and then do the normal steps. Okay? And if it was the other way around, I guess you could do all the regular steps, a bunch of stuff to cancel out because it's just going to be right here, right? If it wasn't given H, because that's its parent, but given B or something, now you have to do that stuff. If it was just given its parent, you can just look it up. Okay? All right. So that gets on camera real quick. If you have something that's backwards, so what's the probability of U given H? Doesn't show, sorry. H given U doesn't show up in your tables, so you have to use the Bayes rule, and then you know how to do these parts. So you use the two general methods, find those out separately, and then you just take the three things you got and use this equation and get the thing out. All right, and then last point is going to be about independence. So does anyone need to see the general methods, or can I erase those? So let's say, here's an example I like to give. So this is dependence. Okay. So what if you studied and whether a class was easy might tell you if you got an A+. So you might have some sort of truth table, like studied, easy, and then your grade. And you might say, well, if I didn't study and it wasn't easy, then there's a really low chance I get an A. If I didn't study but it was easy, I had a pretty good shot at getting an A. If I studied and it wasn't easy, okay, not so good, but still better. And then if both are true, then that's awesome, right? So now you can ask things like, okay. So let me talk about the three types of independence before I get into this example real quick. So there's just there's what we call independence by itself, which means that this condition holds. So it means the two events don't really have anything to do with each other. Knowing one of them doesn't help you know the other one at all. Okay, that's intuitively what it means. So knowing one doesn't change what you think about the other. So that's like normal independence. Then we have marginal. So this means like, what's the probability of A given B? So it's like asking, what's the probability that today is Tuesday, that given that it's raining? Well, it doesn't matter if it's raining. It's Tuesday, so here, right? So it's not a very good example. But anyways, what it means is that we don't really care about this B. This B is not giving us any new information. So we can say that A and B are, this is a, and then conditional, yeah. And then conditional independence, something like this. So I'll just quickly mention the fact that there's this thing that is in the notes, and it's some algorithm called de-independence. No, sorry, de-separation. And so deseparation, I personally don't really like it that much just because it's able to tell you whether things are definitely not conditionally independent. So it can say like, these two things are definitely not conditionally independent. But you might feed it like these two and it might just tell you like, well, I don't know, they could be or they could not be. So it doesn't always give you like a yes or no, it can give you like a maybe. So I don't really like it that much. It's a lot of work. You have to draw all these graphs and do all this crap, and sometimes it's like not what you wanted anyway. So I kind of don't like this approach, but you can look at the notes and see how that's done if you want to learn that way. I'm going to talk about a more intuitive way that I think is, I think for like really hard problems, like with a giant Bayes net, this deseparation thing could be useful, but I think the ones we give you no 3, 4 are a lot easier to solve just using your intuition. So something I could say is getting an A independent of it being easy. So let me ask you this. If I asked you, what's the chance that you're going to get an A+ on that test? Would your answer change if I told you the test was going to be easy? Right, so let's compare those two things. Probably that you got an A+ versus probably your plus in easy. So we can actually work these out and use our general methods to come up with numbers. But just from looking at this, I can tell that when it's probably getting an A without any other information is going to be it's going to be less likely than if I knew it was easy. Just by looking at these numbers, I can kind of tell that, right? Because whenever we change easy to be true and we keep S the same, our chances go up. That's an intuitive way of seeing that, right? So this one is greater than that one. So I'll just put that here. So that definitely tells us that they're not marginally independent, right? So these don't look very independent. But now I could ask you something like, what if I told you that you studied? Does that help you figure out whether it was easy? The test is going to be easy? You can just intuitively know that, like, no, it's probably not, right? But even just looking at this graph, you can kind of tell it's not going to really lead you anywhere. But now, if I told you something like, you got an A and you studied, does that help you know if it was easy? Or what if I told you the opposite? What if you didn't study, but you got an A? Does that tell you something out of being easy? So now you have a higher chance of being easy, right? And so you can go through your children like this. So let me come up with I think I need a slightly more complicated one to drive this point home. So let me just do something like that. So here's what I'll try to say. So this was studied. This was easy. Maybe this is like whether it's spring semester or not. And this is like if you were happy or something that day, right? Just a bunch of things that you can model with this. And now, what I might want to ask you is, what's the probability that you studied given, let's make this false so it's half. It's probably you studied given that it's fall and that it was easy. And so now the question is, can I just remove one of these? Like maybe I don't care about whether it's easy because I just know that it's fall. That can tell me something, right? Maybe that's enough to make a good guess. But what I want to leave you guys with as a strategy I use is try reaching this from these without going through any of the things in here. So for instance, can fall get to studied without going through these notes? Yes, it can just go straight there, right? can easy get to study without going through these nodes. Yeah, it can go this way. So there's like a path for it to get there, right? So these things are all well and good, but what if I included like happy? Happy is only going to help us make a guess about whether something was easy. But we already know if it was easy or not. We don't have to guess anymore. We know, here it is, it's a given. And so this doesn't really matter. I can just get rid of this. And so I can come up with the expression that these two things are equal. So that's intuitively how I do it from looking at it. I kind of just try to get there without going through other things. Because whenever I go through something, I'm going through information I already have and trying to make a guess. But I shouldn't be making a guess. I already have that information. No need to make a guess there. Okay? Okay, cool. Let's see. Oh, yes. Okay. Then there's one last tiny part, which is just sometimes they'll ask you about the number of parameters. So what this means is how many things do you have to specify in order to cover the entire space of probabilities. So for instance, for this H, A, U, S, and B, imagine we didn't know what the neural net looked like. How many things would we have to specify in order to get like all the probabilities? So we might need to specify what H, A, U, S, B looks like. And we also might need to specify what H, A, U, S, and not B looks like. And we also might need to specify what H, and A, and U, and S, not S, and B looks like. And we can keep going. And we get a bunch of these. And now how many things are there? Well, for these things that are Boolean, so right now we're only looking at Booleans. There could be more states in other examples, but for Boolean things, we have 2, 2, 2, 2, 2. This thing looks sort of like 2 to the 5th. That's like about how many parameters we have, on the order of that, how many parameters we have to specify. So we have to give these things numbers. And then we can ask any question and answer any question like, what's the probability of H? Now that we've given these 2 to the 5th numbers, now we can answer this. If we hadn't given one of these, maybe it would be impossible to tell you what this is, right? So that's what it means for the number of parameters. But this neural net, the structure of it, actually encodes some of that information for us. And so let me ask you this. Given this structure right here, we already proved that just by having these truth tables, these conditional probability tables, we can answer any of those questions. And so how many numbers did we specify? We actually only had to specify 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we actually only had to specify 10 things. Because the topology actually kind of held some of that information for us, so we didn't have to just specify them out in a giant chart. So we only have 10 parameters in our example. Okay? And you can just count the entries into conditional probability tables. And now notice I didn't include the ones, the ones where like B is false, those columns over here. Because once I specify this one has no choice but to be 0.85. So it's not something I have to like additionally specify. It's just like implicitly known. Okay? And so once you have that and you have all your, so once you have your, let me say that a little clearer. Once you have your Bayes net drawn, you just have to specify these probabilities in the tables, and now you can solve for any probability relating to these. Okay? So that's like kind of the power of it. Okay, so that's Bayes nets. So there they are. I hope you guys can answer any question about them using like the general methods. And what I mean by questions is things like this, whether the smiley face matters or not, what the numerical values for these things are, how to do that. Okay. And then next time what we're going to do is we're going to take all these concepts and put them together and come up with some sort of classifier that's going to fit into our supervised learning algorithms bags. And that's it. Last quick little logistical note is I'm pretty sure we're going to cancel office hours because it's Thanksgiving. So I hope you guys are all with your families and stuff. So no office hours this Friday for me and Thursday for other people. And then hopefully what we're going to try to do is move office hours next week to be before the exam so we can hold like quiz reviews. So I'll probably end up moving my office hours next week to like Tuesday.